Thank you for your introduction and welcome to my presentation about laser additive manufacturing, material and quality classification. I will start with some words about the process, the aim, and the methods we used. Then I will present you spectral analysis results and classification task results. So first to the aim of the study. We want to evaluate and characterize material and quality of a laser additive manufacturing process just by acoustic sensors. Why we want to use acoustic sensors? They are cheap and they are easy to apply to existing system because they only need passive monitoring. This is a collaboration between Oscar PLT, the University of Technology in Ilmenau, and the Fraunhofer Institutes, IDMT, IWU, and IKTS. We investigated a pro-focus laser system mounted on a KUKA industrial robot arm. We used a laser power of 1 kilowatt, wire feed rate of 0.9 meter per minute, and a wire diameter of 1 millimeter. This slide shows you all experiments we performed in that small study. You see on the right side of the slide some photos of the produced layers which we used for testing the principle. Here we used two different materials, two different additive materials. One is a steel wire and second is a copper wire. We also applied two different quality settings. First is a good process, which is the normal operation of the system. And second is an unstable process where the focus spot is 1 millimeter above the good laser focus spot. This might result in problems in connecting the material with the underlying workpiece. And in real manufacturing, this incorrect focus spots may occur by multiple layers which are placed over each other. All in all, we produced 32 separate layers. Each layer has 14 lanes of melted material, and care was taken to alternate between good and unstable layers to not get a prediction in the data. We placed the layer on 4 different workpieces. The workpieces are of steel material, and there are 8 layers per ground block. Here on the slide, you also maybe seen that there's a slight color difference between block 0 and 1 on the one side, where we use the steel material, and block 2 and 3, where we use the copper material. Now I come to the sensor configuration. We used 3 sensors. One is a microphone from Microtech FL with a preamplifier. You can see here on the photo of the slide in the left lower corner. Sensor 2 and 3 are 2 structure-bound sound probe sensors from Sonotech, and sensor 2 was placed on the work surface a little bit away from the process here on the left side of the photo, and sensor 3 was directly on the workpiece behind the process. For recording, we used a soundbook from Sinus Messtechnik with a sample rate of 204.8 kilohertz and a resolution of 24-bit. After recording, we cut the signals to the real process time and performed a short time Fourier transform, as well as a HiCAD at 70 kilohertz. Finally, we framed all signals of all layers into segments of 0.1 second length, and these frames we used as classification units. So classification does not decide on the whole layer, it decides for each 0.1 second segment length so that we in the future are able also to detect small unstable process segments. We also performed 3 different classification tasks. One is material classification, where we want to differentiate between steel and copper wire. This is useful later in multi-material processes. The other 2 classification tasks are quality classification, where we want to differentiate between the good and the unstable process, one for steel material and one for copper material. For modeling, we used a convolutional neural network with 4 hidden layers and including 2 convolutional layers. For training and evaluation, a stratified cross-validation was applied with 5 folds, and we made concern that we do not split the data of one layer into training and test. So all data of one layer is either in the test set or in the training set. And classification was applied on that 0.1 second segments. For evaluation matrices, we used the balanced accuracy and the F1 score. Before I come to the classification results, here are some spectral analysis results. It's a spectrum comparison between the different layers. I've plotted the time averaged signal for each layer. So each column in that diagram is one layer, and you may see that there's a strong variety between the different layers in frequency response. The layers are grouped by material and by the material and the blocks, and the quality of the layers, so the unstable or stable quality is marked with color on the x-axis. So by looking at the diagram, you may see that there's no clear difference between layers of different material or different quality. And the only thing which is obvious is that there's a difference between block 0 and the other 3 blocks in the higher frequency range of about 50 kilohertz. Now I show you the same spectrograms, now grouped by material and quality. So on the left side you see the steel wire, and right the copper wire, and always the good and the unstable layers left and right. But also you see that there's no distinct feature in frequency range to classify the material or the quality. Still with the neural network, we reach some results. Here on the slides, you see the first classification results. One example, it's the material classification with sensor S1. And you see a confusion matrix, which shows for steel and copper wire material, the number of time frames classified as steel or copper. From that confusion matrix, we can calculate a balanced accuracy by the relative amount of correct samples per class of 86%. But you may see that in the white column, the copper wire has a little bit higher recognition rate, and the steel wire has a little bit lower recognition rate. We also calculated a confidence interval, the 95% confidence interval, which is in that case ranges from 75 to 94%. It's relatively large. This is caused by the fact that we use the number of layers as dataset size for the calculation of the confidence interval, and not the number of time frames, which are much more. We think that it's more realistic to use the number of layers here because we have that strong variation between different layers. So that slide shows you all results, all balanced accuracies for the 3 different tasks we performed and the 3 different sensors. You may see that the material classification on the left side produces the best results. Here for all sensors we get balanced accuracy above 80%. Sensor S3, which is direct on the workpiece and nearest to the probe, to the process, reaches even 99%. Quality classification on the middle and right side of the diagram is more challenging. With steel wire here, the best sensor S1 reaches 81%, and with copper wire, the best sensor S2 reaches 75%. We also tried sensor fusion for late sensor fusion and early sensor fusion, but the results are not, but we don't get better results than for the best sensor. One score results are really similar to the balanced accuracy results. There's no big difference. So the conclusion is the same. Now I come to the end of my presentation. We deposited 4 layers and saw different coloring between steel and copper wire. In spectral analysis, we found that there's no obvious difference between different materials or different qualities of the process. But there's a lot of variation between individual layers. Still, it's possible to set up a classification, and material classification is really good, possible only by sound, best with the closest sensor. For quality classification, there's a high variance in accuracy and F1 scores, but some sensors shows promising results. So we are looking forward to improve the results with more experiments and a larger study. And we want to set up an industrial-ready system for process monitoring and optimization. So thank you for your attention.